To introduce Professor Phillip Griffiths from the Institute of Advanced Studies, and he's going to be talking about positivity of vector bundles in Hodge theory.
Thank you, Ernesto, and thanks to the organizers for the invitation to come to this meeting, great meeting, and give a talk. The topic that I will be just talking about, let me see, yeah, maybe this does it. Does that go to the next page?
This is not working, let me check just tiene que tener una cosita aquí, ¿verdad? ¿Y dónde está? Aquí. It's not connected, of course. Now we're in a much better position. Now the batteries are working.
Methods have historically, and I think also recently, had interesting applications to algebraic geometry. So I will try to explain a little bit of the differential geometric background motivated by some algebrogeometric questions. First, just some introduction, and then some general comments about holomorphic vector bundles over complex manifolds, especially projective algebraic varieties, and what is meant by positivity in the differential geometric sense. And then a particular interest, I think, in recent years has been metrics and their curvatures when you have singularities. So I'll talk a little bit about this. Especially in Hodge theory, the singularities have a very nice structure, and try to explain that. And then talk about two applications. One is the Hodge line bundle and the application to moduli of that one. And then the other is the Hodge vector bundle. And there the main application is to a classic problem, the Oaxaca conjecture. So a basic problem in complex geometry is to construct global holomorphic objects. In sort of classical several complex variables, you wanted to construct global holomorphic functions on domains in Euclidean space or non-compact complex manifolds. In algebraic geometry, you want to construct holomorphic sections of vector bundles. So both of these problems involve curvature. For the several complex variable problem, the curvature appears in the Levy form of an exhaustion function of the domain, saying the Levy form, if it's positive definite, says the domain is strongly pseudoconvex and therefore a Stein manifold. In algebraic geometry, the line bundle or the bundles themselves have metrics, and the metrics lead to curvature, and the sign of the curvature then has algebrogeometric implication. In particular, algebraic varieties typically come in families, and in Hodge theory, one has vector bundles arising from a family of algebraic varieties, sort of linear objects measuring the geometry of the fibers. When the varieties in the family acquire singularities, the metrics and their curvature will acquire singularities. So that's the reason for the presence of studying singularities of the metrics and curvature that arise from Hodge theory. Typically, the curvatures in algebraic geometry tend to have a sign, say non-negative, and they have singularities. So in this talk, I'll talk some about generalities, about the singularities, and then the two applications, the one I mentioned for the Hodge line bundle will be to a very interesting completion of the image of what's called the period mapping, the thing that associates to each algebraic variety its Hodge structure. Look at the image of that map and complete it into something compact. And the Hodge line bundle leads you to what will be defined to be the Satake-Bailey-Burrell completion of the image of, say, the moduli space under the period map. The Oaxaca conjecture, that has to do with the Kadara dimension. The Kadara dimension measures the dimension of the space of sections of powers of the canonical bundle, the growth of the dimension of the spaces of sections as you go to higher powers. And the conjecture that was posed by Oaxaca and that was proved by Vivek says that when the general fiber is of general type, you have this sub-additivity problem. So the first case, we'll use the positivity of the Hodge line bundle. That's the Satake-Bailey-Burrell completion of the image of a period map. The second, and what it will show, is that Hodge theory, this was really the underlying problem. There are these mysterious moduli spaces that were defined and proved to exist for varieties of general type, proved by Kolar, Shepard-Barron, and Alexiev in the 80s and 90s. They gave a construction and proved that there's this canonical completion of the moduli space, but there are no examples of what the boundary looks like in non-classical cases. So Hodge theory gives you a way of associating some more easily understood object to the limits of smooth, say, surfaces of general type as they acquire singularities. It's a way of organizing the structure of the boundary of moduli. And I'll give a couple of examples that illustrate how that works for really the first two algebraic surfaces of general type that one comes across classically. As far as the Oaxaca conjecture goes, it organizes the general classification of algebraic varieties. The first step is by Kadara dimension. So maximum Kadara dimension, that means you have the most sections of powers of the canonical bundle that are allowed. That's general type. That means the variety is realized by some pluricanonical map into a projective space. Kadara dimension 0, those are Calabi-Yaos, things like that. Kadara dimension minus infinity, those are the Fano's rational varieties. The Oaxaca conjecture deals with a fibration and you assume that the Kadara dimension of Y is its dimension, so it's of general type. I'm sorry, yeah. The Iotaka fibration says if you have any variety X, it fibers over something that is of general type, whose general fiber has Kadara dimension 0. So it sort of organizes the classification into these two cases, and this one is special. It's treated differently. Okay. So that was the rationale for the Iotaka conjecture, and it's the basic result, structural result about in the classification of varieties that one uses to get started, if you like. Let me talk a little bit now about positivity of vector bundles. So we imagine that we have a holomorphic vector bundle over a complex manifold, and if you have a metric in that bundle, there's canonically associated to it a connection. It's a differential operator from C infinity sections to 1 forms with values in the bundle. The 0-1 part of the connection is the D-bar operator. That gives you the holomorphic structure on the bundle, and the connection is compatible with a metric. It satisfies the Leibniz rule. It's like in Riemannian geometry, there's a unique torsion-free connection that's compatible with the metric. That's for the tangent bundle. In complex differential geometry, for any holomorphic bundle with a Hermitian metric, there's a canonical connection. That's the Chern connection. The curvature is a differential form of type 1-1 with values in the endomorphism, so it's a matrix valued 1-1 form, and it has this Hermitian symmetry coming from this property here. Locally, the metric is just a Hermitian matrix. The connection form is H inverse DH, and the curvature is D bar of the connection. So it has particularly nice, simple expressions in local coordinates. The curvature form is the basic invariant of the curvature matrix. And it's a form that involves a vector in the fiber of the bundle and a tangent vector. And the definition is that you apply the curvature matrix to the vector E in the fiber, take the inner product with E, that's a 1-1 form, and evaluate it on the tangent vector wedge's conjugate. So it's a biquadratic form. Okay. That's the basic invariant that measures positivity of holomorphic bundles over complex manifolds. If we have a line bundle, then the curvature form, 1/2 pi I times it, is the Chern class of the line bundle. More generally, if you take the elementary symmetric functions of the curvature matrix, the trace, determinant, all of those give you the Chern classes represented in de Rham cohomology. So the bundle's positive if this form is positive, and semi-positive if it's bigger than or equal to 0. One of the first examples that you come to of holomorphic bundles is the universal bundles over the Grassmannian. So you're looking at K-planes in Euclidean space, and there's the universal subbundle. You take its dual. You do that to get positivity, or the universal quotient bundle. So the fibers of the universal subbundle are just the linear space itself. The fibers here are the quotient spaces. This bundle is always non-negative, and it's positive only in the case of projective space, either lines in Euclidean space or hyperplanes in Euclidean space. All the intermediate Grassmannians are positive semi-definite, but not positive. Sort of the explanation is this, that the tangent space to the Grassmannian is just gotten by seeing what happens when you perturb a plane to first order and project in the quotient. Okay. So for the two planes in 4 space, that's really the lines in projective 3 space. And a tangent vector, this is the picture. That's a line in P3. You perturb it, and one of two things happens. Either it meets the original line in some vector, or it's disjoint from its skew. Okay. The curvature form is the square norm of the value of this tangent vector as a homomorphism mapping this space to this. They both have metrics. So the curvature really is measuring, it's non-negative, and it's 0 only when to first order the line, when you displace it infinitesimally, meets the line that you started with. Okay.
Where is it not positive?
Excuse me?
When the line is like this? So
if the lines are skew, it's positive on a...
But when it's not, so when it's not positive?
When it's not positive, that means that if you infinitesimally displace the plane, it intersects the plane you started with. Okay? So it's the rank of the matrix gives you the sort of nullity of the curvature form. The interpretation of the curvature form, the standard one is to look at the corresponding projective bundle. The fibers of the projective bundle are the duals of the projective space built on the dual vector space. So the project P of E means the one-dimensional quotient of the fibers in E. Okay. You do that so that the sections of this bundle, this line bundle, are the same as the sections of the original vector bundle. Okay, just that's what one-dimensional quotients reflects. So there's a tautological line bundle whose fiber is just the line, the whole line corresponding to the direction in question. It has a Chern form, so it's a line bundle on a compact complex manifold. And it's positive in the fibers because on the fibers you just have the standard positive bundle on projective space. So this form is positive in the fibers. In the horizontal space, so since it's positive in the fibers, you have a horizontal space, which is the orthogonal complement. And that's the horizontal space. You identify the bundle with its dual using the metric, and this is the formula for the curvature form. So the positivity of the curvature form of the vector bundle reflects the positivity of this line bundle upstairs in the horizontal directions. So this is just restating for projective space the Grossmannian example. Second example is if you have a family of smooth algebraic varieties. So those are, I'm calling them XT, the fibers fibered over some base space. Then there's the Hodge bundle. Think here really of family of algebraic surfaces, because that's the main example that we'll be discussing. The Hodge bundle, the fibers are the global holomorphic two forms along the fiber. Is as a bundle over B, it's the direct image of the relative dualizing sheaf. Has a metric gotten just by taking a holomorphic two form, wedge its conjugate, and integrating it over this algebraic surface. Okay, times some number to make it positive. Okay. So that's the Hodge vector bundle with its Hermitian metric. What about the curvature of this bundle? Well, the fiber is part of the second cohomology group of the surface. And the second cohomology group has a cup product, so you can look at the orthogonal. There's a Kodaira-Spencer map from the tangent space to the parameter space into the homomorphisms of the 2-0 part of the cohomology, this, to the orthogonal modulo this, just like in the Grossmannian. Using the metric here, the curvature form is just the norm squared of this. So the curvature is measuring the extent to which the space of holomorphic two-forms on the surface move around in the cohomology of the surfaces. The cohomology of the surfaces are a fixed vector space. They're all the same topological surface. But the holomorphic two-forms will move around in the cohomology of the surface, and the curvature of the Hodge vector bundle measures how much they move around. Okay, so it's always non-negative, and this gives you an algebraic geometric interpretation of when it's zero. So if you have a positive vector bundle, then the line bundle over the projective bundle is positive, and by Kadara's theorem, the classic Kadara theorem that really started the whole relationship between positivity in the differential geometric sense and the existence of sections of powers of a bundle or line bundle. Kadara said that if it's positive, then it's ample. So that's the interpretation of positivity, that this tautological line bundle should be ample, so powers of it have lots of sections, so powers of the symmetric powers of the bundle have lots of sections. Okay. So positivity suggests sections, and the measure of the amount of sections of any line bundle is gotten as follows, that you take high powers of the line bundle, use the basis for those sections as homogeneous coordinates, the usual way of mapping a space to a projective space by taking sections of a line bundle, gives you a rational map. And the Kadara-Iyataka dimension of the line bundle is either how fast this thing grows as a polynomial in the power of the line bundle, or more geometrically, the dimension of the image for large powers of the line bundle. So a line bundle is said to be big if the Kadara-Iyataka dimension is equal to the dimension. That means it has lots of sections, and that's a birationally invariant notion, bigness of a line bundle. Vector bundle is big if the corresponding tautological line bundle is big. That means that high symmetric powers of the bundle have lots of sections. So the basic theorem is that the line bundle is big if its curvature form is non-negative and the top exterior power is positive on an open set. So the curvature form should be positive semi-definite. It's a Hermitian matrix. Should be positive semi-definite. And on an open set, it should be positive definite. For a vector bundle, the curvature form should be non-negative, and on an open set upstairs in the projective bundle, positive. This theorem was conjectured by Grauert and Riemenschneider, is proved by Hsu and de Maillet and others. And it's the sort of basic metric criteria for bigness of a line bundle or a vector bundle. So if one wants a bundle with lots of sections, one wants to find criteria for bigness. Historically, positivity is too strong, and just semi-positivity for vector bundles is too weak. You can take a vector bundle that's positive and add to it a trivial bundle, and that then is still semi-positive. Okay? So classically, positivity was too strong, semi-positivity too weak. One wanted some additional criteria that tells you that you have lots of sections, but it's weaker than positivity. And the result is this, that if it's semi-positive and if the trace is positive on an open set, then the symmetric powers are big when you get past the rank. So what it's saying is that for symmetric powers of sufficiently high degree, You have to get up to the rank of the bundle, and from there on, you get bigness for that vector bundle. The proof is really an observation that the curvature form on a symmetric product is just the sum of the curvature forms on these factors. And if the trace is positive, then one of these things has to be positive if you take a basis for the fiber. So it's really an observation. So, for example, if you have a submanifold of the Grassmannian, then the symmetric powers, not the pullback of the universal quotient bundle, but symmetric powers of it become big once you get past the rank. For the case of a family of algebraic varieties, once the Kodaira-Spencer mapping becomes injective, that's the condition on the trace of the curvature, then you get bigness for powers of the symmetric powers of the Hodge bundle. So for example, for abelian varieties, if you look at just any sort of Shimura variety, then the Hodge bundle is of rank G, and the Kodaira dimension of the Hodge bundle is 2G minus 1. It's never big. It doesn't have a lot of sections, powers of it. Okay? But once you take the second symmetric power of the Hodge bundle, that becomes big. More generally, if you have a family of algebraic surfaces, the Hodge bundle itself will not be big. But if you take the symmetric power equal to the Hodge number H20, the geometric genus, those symmetric powers from there on become big. Okay? So that's the sort of nature of this result on the previous slide. Okay. In the case of the Hodge bundle, one has to deal with the singularity. So the parameter space is typically a quasi-projective variety. You can complete it to a projective variety with singular varieties over the divisor at infinity. You can always take that to be a normal crossing divisor. And an interesting question is, okay, you have the Hodge metrics for the smooth surfaces. The Hodge vector bundle extends canonically. There's a canonical extension of that to the whole parameter space. I'll explain what that is in a moment. What about the metric? And especially what about the curvature and the churn forms coming off of the curvature? How much singularities do they have? So for this, we will complete the parameter space to a smooth projective variety where the divisor that you add is a divisor with normal crossings. Just the usual picture. With strata, just gotten by intersecting the irreducible components. Locally, it's just a product of punctured disks and disks with coordinates, say T's that are coordinates in the punctured disk and W that are coordinates here. So you have a nice sort of local picture at infinity. Here, the differential forms, the natural ones to use as the frame are not the differentials of the coordinates, but for the punctured disk, use the Poincare coframe. Okay, so that's dTi over Ti times the log of absolute of Ti. And the minus sign here makes this positive because you're near the origin. And they're conjugates. Okay. The Poincare metric is just the product of these things and their conjugates. That's the usual Poincare metric on the punctured disk viewed as a quotient of the upper half plane by translations. Okay. It has many beautiful geometric properties. One of them is that the geodesics are the straight lines going to the origin. The metric is complete, so the length goes to infinity in the Poincare metric. On the other hand, the circles that go around the origin, those lengths go to 0. As the circle shrinks to a point. So the product is just the area, and the punctured disk has finite area, okay, in the Poincare metric. So if we're going to consider a holomorphic vector bundle on the compact thing, which has a metric over the open part. So the metric is smooth except along the divisor at infinity. The example being, of course, the family of algebraic varieties. You complete it using the Abramowitz-Karo semi-stable reduction. So it locally looks like a product of normal crossings at infinity. And sort of the simplest coordinate description that gives you some feeling for what the singularities of the Hodge metric look like is just this picture here, a little piece of a Riemann surface that acquires a double point, a node at the origin. This differential is what the holomorphic differential on the smooth algebraic curve looks like in the limit. And when you evaluate the integral along this dotted curve, so you have a cylinder and you just have the straight line along the cylinder, you get a log term. So that means the area of this holomorphic differential, the integral of the thing wedged its conjugate, blows up logarithmically. So the metric in general is said to have logarithmic singularities if in terms of a local holomorphic frame, the lengths go to infinity logarithmically, at most logarithmically. The connection and the curvature, when you express them in terms of the Poincare frame, are Laurent polynomials in logarithms with coefficients that are real analytic functions on the whole thing, on the whole product of disks. Okay? So it's saying that the singularities of the metric are at most logarithmic. The singularities of the curvature are like the Poincare metric times logarithmic stuff. And the basic theorem here is that the Hodge bundles for a variation of Hodge structure, so think of a family of surfaces. The canonical extension is you just call something holomorphic across the divisor at infinity if its Hodge norm goes to infinity only logarithmically. Algebra geometrically, you just fill in the vector bundle by putting in the direct image of the relative dualizing sheaf along the divisor that you at infinity. So it's the natural algebra geometric extension. Okay? So that's the canonical extension, and the Hodge metrics have logarithmic singularities. Okay? So for example, their Chern forms, the Chern polynomials in the curvature will look at most like the things that you get from the Poincare frame with stuff in front that blows up at most logarithmically. That's fairly crude because if you just take the Poincare metric and multiply it by log of t, you don't get finite area anymore. The area goes to infinity. Okay? So you'd want Laurent. So a much more subtle result than the one on the previous overhead is just a reformulation in metric terms of what's called the theorem on regular singular points of the Gauss-Manin connection. And it's just a translation into these terms of that algebra geometric statement. Much more subtle is the theorem of Catani-Kaplan-Schmidt that says that these Chern polynomials are they're differential forms that are in L1. They're integrable. So you take the Poincare thing, if you multiply it by a Laurent polynomial in the logs, you at most have stuff in the denominators, not in the numerator. Okay? And once they are differential forms that are integrable, they define closed currents in the sense of currents are like distributions but differential forms. And those closed currents represent the Chern classes. So it's a very beautiful theorem from the 80s by Catani-Kaplan-Schmidt. It's a very subtle analysis that goes into this. Okay. The easiest possibility would be that the Chern forms have bounded coefficients in the Poincare coframe, but when you have a product of two or more punctured disks locally. That doesn't happen. It's much more subtle. So what about these churn forms? They are currents, so they're like differential forms, but their coefficients are distributions. Okay, the distribution is a linear function on C infinity functions. Okay, they're in L1, so you can integrate those coefficients against C infinity functions, but they can certainly be singular. The two classic problems with distributions on a manifold are that you cannot multiply them. You can do everything with distributions except two things. Multiply them, and you can't restrict them to submanifolds. Okay? So for example, the Dirac delta function is a distribution. You can't restrict it to the origin. Doesn't make sense. Okay? So a distribution in general on a manifold has a singular support. The singular support is a closed set such that in any open set in the complement, it's a smooth function. And much more subtle than the singular support is the wavefront set, which is in the cotangent bundle, restricted to the singular set. Okay? The wavefront set in analytic terms means that you look at the Fourier transform of the distribution. That thing takes place in the dual vector spaces, so in the cotangent bundle, and you look at the growth of the Fourier transform as you go to infinity, how fast it grows. So rapid decay at infinity is C infinity, and so on. Okay? That's the wavefront set. That was introduced, among other things, to be able to multiply distributions. You can multiply them if their wavefront sets are transverse. Or restricting distributions, you can restrict a distribution to a submanifold M prime in M if the submanifold is orthogonal to the wavefront set. Okay? That wavefront set is in the cotangent bundle, so it's really something saying that the singularities of the distribution occur only in the conormal bundle of the submanifold, not along the submanifold. So the definition of mild singularities is that, I'll just give the informal definition, that you can multiply them and restrict them. And there's a formal definition, but operationally it means that you can multiply the Chern forms. So this is what is meant by mild logarithmic singularities. You can multiply the Chern forms just as if they were regular smooth forms. Just do it formally and you get the right answer. And secondly, that you can restrict them to the strata that you've added. So operationally what it means is that the Chern forms of the extended Hodge bundles behave in all practical respects as if they were smooth. They're not, but they behave as if they were smooth. Even better, what you'll see is that the singularities contribute, they're integrable, but they contribute positively. So the second sort of heuristic is not just that the Chern forms behave like smooth forms, but secondly, they contribute to the positivity of the Hodge bundle. Okay, the amount of singularity they can have is bounded, but the more singularity they have drives up the positivity. So they help you rather than hurt you. So the applications of it's really of the singularity property as much as anything of the Chern forms. The first is to moduli the Hodge line bundle. If you have a family of smooth varieties, that gives you a period mapping that sends each point in the parameter space to the polarized Hodge structure. That's in the period domain factored by monodromy. Classically, what that means is you take the period matrix of the integrals of the holomorphic differentials and interpret that sort of in geometric terms. So the period matrix of a Riemann surface is a point in the Siegel upper half plane of G by G symmetric matrices with positive imaginary part, and so on. Okay, so that's D is the space of all polarized Hodge structures with given Hodge numbers. In a family of varieties, you cannot identify all of the fibers topologically. You can only identify them topologically up to the action of monodromy. You take a cycle, a homology class, and follow it around a loop. All of these are smooth manifolds, so topologically they don't change. When you come back, the cycle that you started with will have changed. It's the action of monodromy. It's just like if you have a branch covering, just of an algebraic curve over one algebraic curve lying over another one, a branch covering. The cycles over the fibers are just the points. You go around the branch point, those interchange on the sheets. That's the monodromy. Okay, that's a monodromy on H0, zeroth dimensional homology, and run that, jack that up to all the homology groups. That's what monodromy is. So you have this period mapping that reflects how it reflects an invariant of the algebraic variety given by its Hodge structure, its period matrix. Along the strata, as the variety acquires singularities, there's again a detailed analysis of just what happens to the Hodge structure. It's done by Lie theory, and it's again in the Catani, Kaplan, Schmidt paper and others, but that really is the basic work back in the 80s. So one has a good picture, Hodge theoretically, of how Hodge structures degenerate. You want to use that to say, okay, we know how the Hodge structures degenerate. Let's work backward and see what that can tell us about how algebraic varieties can degenerate. What sorts of singular things do you add on when you complete moduli spaces? So they get what you call a limiting mixed Hodge structure. A mixed Hodge structure is like a successive extension of Hodge structures. Okay, so think of lower triangular block matrices. That's a mixed Hodge structure. The associated graded are just the block diagonals. So the simplest way to imagine that is an algebraic variety, when it becomes singular, has singular strata. Those strata are smooth varieties. They have Hodge structures, and those are the sort of beginning part of the data that's in the limiting mixed Hodge structure. So you get, from the associated graded period mappings on the boundary, the Hodge line bundle, which is just a determinant. So when you take associated graded, it just behaves like a direct sum. That's the Hodge line bundle on the boundary. The Chern form extends. That was the theorem before. And the thing about the singularities of the Chern form says that if you take this singular differential form and restrict it, which you can do, what you get is the Chern form of the limit. So it's the, if you like, the limit of the Chern forms is the Chern form of the limit. It's the way to think of it. Okay. So if we let M be the image on the period mapping in here, this is the image of the strata, then the natural thing to do is just glue on to the image of the period mapping what the different boundary strata go to. And the theorem then is that this has the structure of a compact, complex analytic variety, and the Hodge line bundle is ample there. It's not just positive, semi-definite, it's ample. So that gives you the Satake-Bailey-Burrell completion. What you've done is take this family of algebraic varieties, look at their Hodge structures, okay, see what the Hodge structures, what you have to add on to the Hodge structures when the varieties degenerate. And what you get, the way to describe that algebraic-geometrically is take proj of the Hodge line bundle. That's the ampleness thing. So to give a couple of, well, let me just make a comment about Satake-Bailey-Burrell. Classically, Satake-Bailey-Burrell first dealt with abelian varieties. It was the standard minimal compactification of the moduli space of abelian varieties or Shimura varieties. Then K3s. For K3s, there are 3 types of boundary components. Those, by the way, are classified by what happens to the limiting mixed Hodge structure. And there, the Satake, Bailey, Burrell is just type 1 are the smooth ones, type 2 are the elliptic ones. That is dimension 1. The moduli space is dimension 19, dimension 1 for the things which are of type 2. And then the one singular point, the maximally degenerate one, is just a point. Okay? So that's the Lie theoretic construction, the Satake, Bailey, Burrell. It's the minimal compactification of quotients of bounded symmetric domains by arithmetic groups. You're not going to get away with anything like that once you get out of bounded symmetric domains, once you get in the non-classical case. Okay, the period domain is no longer Hermitian symmetric. You can never map to an open set. Monodromy groups need not be arithmetic. They can be these thin groups that are of infinite index in an arithmetic group and so on. So the world is completely different once you get out of the classical Hermitian symmetric case. So you have to do the completion of the image of the period mapping in some different way. Okay, and that's what this result is about. So for the Kolar, Shepard, Baron, Alexiev moduli space for surfaces of general type with given Hodge number H20, H10 is the number of holomorphic 1 forms, and degree of the canonical bundle, which is positive, there's a minimal canonical compactification. So given a family over the disk, there's a unique way of filling it in by Kolar, Shepard, Baron, Alexiev. One knows what the singularities of that limit are. Okay. So that's a sort of local description of what the singularities look like. One knows globally that the canonical bundle of the singular thing, suitably interpreted, should be ample. This is like stability for curves. But one doesn't know globally what those surfaces look like. So that's what one would like to use Hodge theory to understand. So the first 2 surfaces one comes to that are non-classical are when PG is 2. They're regular, and C1 squared is either 1 or 2. These were analyzed in a very nice series of papers by Franciosi, Pardini, and Rolinski. And here one first sees what the boundary in the space of Hodge structures looks like. What sort of limiting Hodge structures do you add on? The picture of what you have to add on is these are Hodge theoretic boundary components. And one thing you notice that's different already from curves, abelian varieties, and K3s is the boundaries, the stratification is not linear. Okay. Whereas it is for the classical cases. And one can say, okay, these are the Hodge theoretic boundary components. Are they realized algebraic-geometrically? And the answer for both of these surfaces is yes, they are. And one has the picture of sort of organizing the boundary surfaces that occur according to where their Hodge structures end up when you take the limit. So going back to this picture here, these are the least singular, these are the most singular. An example, these examples were produced by saying, okay, we know what the Hodge structure looks like in the limit. What surface is going to make that happen? Okay. So here for type 1, you start with a K3. That's the minimal model. It's the minimal model of the desingularization of degree 2, having, so it's a K3 surface with a curve on it. C squared is 2, and it has 1 node. So the K3 in the limiting mixed Hodge structure, the PG went from 2 down to 1. So you have a surface that has H20 equal 1, so it begins to smell like a K3. Okay? That's the graded 2 part of the limiting mixed Hodge structure. The graded 1 part is like the Hodge structure of a curve. That's the Hodge structure of an elliptic curve, but it comes with additional data that comes from the Lie theory. The additional data is 2 points on that elliptic curve. So you join those 2 points and you get this picture. It's a curve of arithmetic genus 2, but of regular geometric genus 1. Blow up that point and you get a surface with a smooth elliptic curve and the exceptional curve. And that smooth elliptic curve has self-intersection -2, so you contract it and you get a surface with a simple elliptic singularity of degree 2. Okay. Though that's the boundary strata for the surfaces that have Hodge theoretic degeneration of type 1, the simplest ones. The other extreme is gotten as follows. I won't go through the Hodge theoretic reasoning, but I'll just give you the end result. You take P2, you take 4 lines in general position, and you join 2 pairs of 2 lines. So just join 1 pair, make a double curve, join the other pair and make another double curve. Okay. There's some discrete data going on because when I glue 2 P1s together, I have to mark 3 points. So you have that choice of how you do that. To actually do this, you have to, of course, blow up these points of intersection because you can't join things if they're intersecting. So you blow up, and then you have to decide how this line is going to meet the remaining 3 lines, the remaining 3 points. You have to select 3 points to go into 3 points. When you do that, you get a surface that has 2 double curves with pinch points, and it has 4 isolated singular points that are cycles. One of length 2, that cycle is a bunch of P1s stuck together. One of length 2 and one of length 4. Okay. So that's the analog, if you like, of taking a genus 2 curve and degenerating it into a pair of P1s joined at 3 points, the dollar bill curve. This is the surface analog of that. The last topic is, that was the Hodge line bundle, how one uses that. The Hodge vector bundle, I think that's a topic in itself. I think because of time, I think I'll just leave that off and stop here. So thank you.
Any questions?
So for the other Hodge theoretic strata, for the limiting mixed Hodge structure gives you clues as to what's the singular variety you should what the singular variety realizes that.
For the most singular one?
Right, exactly.
That's this one here, the P2 with 4 lines.
That's the 4. What's the strata 4 that you labeled it?
That was strata 5. Yeah. The last 2 strata in the picture of strata 4 and 5, the limiting mixed Hodge structures are all of Hodge-Tate type, but they have different Hodge numbers, different dimensions. So you have to look more closely and say, okay, what sort of surfaces have mixed Hodge structure of Hodge-Tate type, but with these types of Hodge numbers? And then you can find one of them is a Del Pezzo with some, a singular Del Pezzo with some gluing that's occurred and so on. Okay, but that's the sort of game one would like to play is, how can the Hodge theory suggest what surfaces to look for? Right. That will give you that thing in the limit.
You have to go and look for it.
You have to go look for it, yeah. I mean, it doesn't, No, it just serves as a guide to how to organize the boundary strata.
Any other questions? Well, thank you very much.
Great, thank you.
We have a 10-minute break.
Sorry, I stole your seat.